Okay, we're on page 7. We're looking at a few examples of circular motion using the formulas found just above on your paper. So in this example, we have a rubber stopper, and this is a rubber stopper that's going to be on a string. So the mass of this rubber stopper has been measured, and its mass is 30 grams. Some information that we'll need later on. And so we found the period of this rubber stopper, so we're swinging it around, and it's kind of hard to measure just once around. That's kind of a difficult thing to measure. And so usually the way you would do this is one person's going to be spinning and counting, and the other person is watching the clock. So we would say, ready, set, go, 1, 2, 3, 4, 5. And so you're going to spin it 10 times while this timer is running, and then after the stopwatch is stopped, then we would calculate the actual period. If we were in the classroom, we'd be doing this, and maybe once we come back, if we have time, we can go back and do all of these demonstrations before it becomes time for something like a test or anything. So with this rubber stopper, we ended up finding that 10 rotations, or 10 times the period, took 4.68 seconds, which means that the period is 0.468 seconds. It takes 0.468 seconds to this travel around once. The radius is measured 92.0 centimeters. And so a couple of things. We want to know what is the velocity in terms of meters per second. Technical difficulties. What is the velocity in meters per second? So we have a formula for velocity. Velocity equals 2 times pi times the radius divided by the period. And we know the radius, we know the period. So we plug in our numbers, there's 2, there's pi. The radius is 92 centimeters, but we want this to be in terms of meters per second. So we'll go ahead and convert it now. So 1 meter is 100 centimeters, and the centimeters will cancel out. Divided by the period, which is 0.468 seconds, and we will end up with units of meters per second. So the velocity is 2 times pi times all of this. Make sure you use the pi button in your calculator. It comes out to 12.35 meters per second. That is the speed, that's the magnitude, but we also have to know the direction. So if we look back at these pictures, the velocity of this rubber stopper is traveling in a circle. Its velocity is tangent to the circle. That is its direction. 12.35 meters per second, tangent to the circle. We can also find the acceleration, and we have a formula for that just above this on your paper. The centripetal acceleration, let's label that, is equal to the velocity squared divided by the radius. So the velocity we found, 12.35 meters per second, we'll square it, divided by the radius, which is 0.92 centimeters. Excuse me, 0.92 meters. It was centimeters, and then we converted it. And so putting this in our calculator, we find 166. And if you look at the units, we have here meters squared per second squared divided by meters, and it comes out to be meters per second squared, which is a typical acceleration unit. What is the direction of this acceleration? Let's look back here. The force is directed towards the center of the circle. The net force, the centripetal force here. The acceleration has to be in the same direction as the force, which means the acceleration is also directed inwards. And we can say 166 meters per second squared inward. We can also find the centripetal force here. And the centripetal force is the mass times the centripetal acceleration. And all we have to do is plug in some numbers. So we know our mass was 30 grams. That is 0.030 kilograms. And our acceleration was 166 meters per second squared. And so we find that the centripetal force is 4.98. Typical units for force is a Newton. We have kilograms times meters per second squared. Units are the same as always. This is going to be newtons. 4.98 newtons. So we found the velocity, we found the acceleration, and we found the force. And this is 4.9 newtons inward. This next example is a car rounding a curve. So here's what we're looking at. So let's draw a picture. Here is a curve in the road. Here's the dotted line. Every curve in the road has a radius. So if you imagine that this is part of a circle, let's say the center of the circle was here. This is the radius of the curve. Every curve has a radius. So here is your car, and it is traveling this direction, about to enter this curve. Here are some values we're going to be given. So your velocity is 20 meters per second. That's about highway speed. You're going about maybe 50 miles per hour here. The mass of this particular car, 1,500 kilograms. And the radius of this curve, 100 meters. So these are some given values that we'll set here. So what we want to know is the centripetal force. We have a formula for centripetal force. If we go back just a little bit, or rather go up your page, centripetal force is mass times the centripetal acceleration. So we know the mass of the car, so that one's not going to be a problem. But do we know the acceleration? We don't know the acceleration per se, but we do know a couple things that go into the acceleration. So let's combine some things. It's not right there. So if we combine this, the centripetal force equals mass times acceleration. And we take this acceleration and sub it in. Now we have centripetal force equals mass times velocity squared divided by the radius. So let's write this down. We had the mass times the acceleration. The acceleration was the velocity squared over the radius. And so here we can plug in our numbers to find the centripetal force. The mass is 1,500 kilograms. The velocity is 20 meters per second. And that's the quantity is squared. And the radius is 100 meters. This is one that you could actually do in your head. You wouldn't necessarily need a calculator. So if you look at this, you have 1,500 divided by 100. Now it's 15 over 1. 200 squared, 20 squared, 20 times 20, that's just 400. So you've got 15 times 400, 6,000, and your units will end up being newtons. So let's have a little bit of a driver's ed lesson here, and let's look at the effects when we double one of these particular things. So, doubling the mass. What is the effect using this formula when you double the mass? So when you multiply the mass by 2, the centripetal force is multiplied by 2. So when you double the mass, the effect is that you've doubled the force. This is something that you can't easily change in your vehicle. If the mass of your vehicle is 1,500 kilograms, unless you have a big truck, you're not going to be able to fit 1,500 kilograms more material in there. So that's going to be difficult. What if you double the radius of the curve? If you double the radius of the curve, you are actually making the centripetal force half. Now, is this something in your control? Can you increase the radius of a curve? Maybe a little bit. And there is such a thing as cornering, where as you approach the curve, you move towards the outside of the curve, and then you follow a line like this. And yes, it increases the turn radius, maybe a little bit, but it's not going to be a big enough effect. And In general, it's a bad practice because you can't always see around the curve. So it's not necessarily safe either. Then there's velocity. What happens if you double the velocity? So if you double this velocity, you'd have 2 here, 2v instead of just v. But you're squaring it. So if you double the velocity, you are multiplying the force by 4. So all of this to say that velocity influences force the most. Bottom line, slow down. It has the biggest effect, and it's the easiest one of these factors for you to change. This centripetal force acting on the car so that it can round the curve comes from 2 sources. Number 1, which we addressed a couple of pages ago, the friction. The friction is providing the force necessary for the car to round the curve. If there were less friction or no friction, the car would not turn. It would travel in a straight line. Think of lots of ice. If you try to turn on ice, you don't have the friction that moves the car. You don't have the friction for that centripetal force, and when you turn the wheels, your car will continue to go in a straight line until the friction is great enough. The other source is gravity. Gravity can be a factor if the curve is banked. So if you're going around a curve on the highway, the road is not exactly level. So let's say that the curve is going to go around this way. And here you're looking at the road surface. Most likely, this road is going to be banked by a few degrees. And this allows gravity to help with the centripetal force. Even a small incline or a small bank is going to make a big difference here. If you were to go to a racetrack like in Indianapolis, what you'll see is the inside lanes where they don't really race, but if they're yellow flagged or something, they'll be driving here where it's flat. But once they get going and they start driving quickly, they move and they don't stay on the flat part of the road. Where it's curved, there's actually a pretty steep bank. And if you've ever been there, it's a lot steeper than you would think. And this is so that the cars can travel along, turning along this curve without spinning out to the outside. And so that's the point of the banked curve.